subtract the embedding of the word Paris plus the embedding of the word Italy, and we look at it in our sort of dictionary, the word whose embedding is closest to the outcome of this embedding, subtract, and addition, we get the embedding of the word Rome, right? And so here are just some other relationships, right? So we take France minus Paris and we add Italy, we get Rome. We do France minus Paris, we add Japan, we get Tokyo, so on and so forth. And this is what's captured by it's just a huge corpus of words, right? Like if you just look at statistical properties, like France, if you just see enough times in the training set, Paris is the capital of France, and you also see Rome is the capital of Italy, that statistical properties gets captured in a 500-dimensional embedding. Do you have a question? Yeah.
Yes. Could you explain again why this embedding has this additive property?
So actually, it's not quite clear why it does have this additive property. And this is a subject of some debate. So this is more of an empirical finding. So it's not 100% well explained exactly why it has this property. I mean, the fact that it has this property is somewhat intuitive because if you can take a huge corpus of words and you look at co-occurrence of neighborhoods of words, basically, which is what this model is looking at. And it's basically saying, I want to find a 500-dimensional, let's say, representation of words, such that words that co-occur a lot within this window have a high inner product. Words that co-occur somewhat have a medium amount of inner product. Words that co-occur very rarely have a negative inner product because it's an exponential model. It's exponentiated, right? Then you could ask, well, does the location of the embeddings have any semantic meaning, right? So there might be some statistical regularity. For example, there might be sentences that say Paris is the capital of France, Rome is the capital of Italy, right? And so what that basically means is that Paris and France are related to capital in roughly the same frequency as Rome and Italy are related to capital, and by some notion of transitivity, they're related to each other in more or less the same way. That's a very hand-wavy explanation. The actual answer is no one actually knows for sure why this is the case. Yeah.
So when you take like the cosine of two words, can you see how close they're related?
It's 500 dimensions. Here's just a third example. So this is a 2D PCA projection of embedding of a bunch of embeddings of countries and cities, and we see that all the countries are over here in the two-dimensional projection. All the cities are over here, and so this sort of subtraction sort of thing, you can see that if you subtract Beijing if you do China minus Beijing, this direction from here to here, you add it to Warsaw, you get Poland. Yeah.
So this grand skip process.
Skip-gram model.
Skip-gram model is not like a maximum likelihood.
You train it using maximum likelihood. You posit. The model is given my current word. I want to predict the distribution over all my neighboring words. I want to model the distribution over all my neighboring words given my center word.
So the standard maximum likelihood would be just like the first two products, right? And this third one is like artificial.
Actually,
because we have like this one slide where.
Right, I'm gonna get to your question in a couple slides. First, I just want to make a comment.
Yeah.
So recall that in logistic regression CRFs, we learned a linear model in some feature mapping, and the feature mapping that you guys used is the word identities, right? Just a vector whose length is equal to the size of the vocabulary, and it's just a unit vector about indicator vectors of whether or not it's this word or that word. You can also use word2vec as your feature representation, which is a much more compact representation than just word identities if your vocabulary is very large. So recall, in CRFs, you have this indicator thing where it's for noun, if it's a noun phrase, you have an indicator if the vocabulary word is fish or if it's sleep, right? Just a single sort of disjoint indicator features. You can instead take this feature representation, replace it with this, where this is the word2vec embedding of whatever word it is, right? And as you use this in the Kaggle competition, and not for CRS but for logistic regression or SVMs or decision trees or whatever, you may have done very well. Yeah.
So wouldn't there be a problem because you gave us a bag of words instead of the whole
Yeah, but this learns, and this is also mapped, and this maps every word to an embedding. So you could just, you can, there's a few things you can do. You can add, like, you can, there's a few things you can do. I don't, So training, okay, so here's how training works. So we're given we're given a whole bunch of sequences of words. So I indexes over sequences of words in our training set. J indexes over locations in each sequence. And again, this is minimizing negative log likelihood. This is maximizing likelihood. And all these models are maximizing the likelihood of a model. Is just what is the model structure. And the model structure here is the skipgram model, which is given any word, I want to predict the neighboring words.
Sure, but so without that sum, that actual minimization is the log of the condition, the whole probability of that occurring, that sequence occurring. Now with this sum, it doesn't have any like meaning anymore. I mean, we can sure do that, but right?
Well, I mean, we're just conditioning. It doesn't have. It doesn't have a joint generative interpretation. Is that what you're saying?
Yeah, before we were maximizing the probability of that sequence occurring, maximum.
Right, but that's a joint generative model. That's a complete generative model of the training distribution. Here, it's no longer a complete generative model of the training distribution. It's a bunch of small model components. Yeah. You know, I see what you're saying, and yeah, it's true. It's not a full generative model of the training set. So I'm running low on time, so I'm going to zip through this, although it is a homework question. Again, one of the limitations of, and of course, you should always read the details of the paper because the slides are going to be sort of overly simplified. But one of the difficulties of this training algorithm is that the denominator again is really expensive. You have to sum over every word of your vocabulary, which could be 1 million, right? In some of these large vocabularies. And so one way to get around this is to reimagine this probability function not as a flat probability, but as a hierarchical probability, right? So imagine a decision tree of paths from some root node to one of the 4 words. So here we have a vocabulary of 4 words for simplicity. So the leaf node is a word, and the probability. So there are probability distributions of every internal node has a probability distribution of branching left or right, and the probability of selecting each word is simply the independent probability of selecting each of the edges as in the path to the one of the leaf nodes. So the probability of given word S prime, the probability of selecting of S, this guy, is equal to the probability of selecting this branch, right? Plus the probability of selecting this branch. The probability of S2 is equal to the probability of selecting this branch times the probability of selecting this branch. So the sum of the probabilities of these 2 branches equal 1. The sum of the probability of these 2 branches equal 1. And so this is one way that we can deal with the fact, avoid having to sum over the entire denominator in the previous flat approach. And so the form of these probability functions are just exponential functions. These are the same form as before. You just learn a parameter vector u that branches between b and c. So if we're given word s, we take the exit vector of word s and we branch with this probability, and then for c it's the opposite, right? So these are forced to be negatives of each other. In the lower branch, sorry that I'm rushing through this, we branch to the word s1 from condition on having reached b as this probability, and we branch the word s2 as this probability, and they sum to 1 because these two are forced to be negatives of each other. The compact formula is the probability, the product of, there are many levels in the tree, not just 2. If n denotes the internal node at level m on the path from the root to leaf node s, it just looks like this form. And the objective looks exactly as before, except that we have a different formulation of the probability functions. It looks like this, and this has complexity logarithmic in the size of the ground set as opposed to linear. Right? So now every word S has one exit, corresponds to one exit vector, and a logarithmic number of entry vectors, because each one of these corresponds to, it is associated with. Of course, even though it corresponds to more than one more than one U, the total number of U's is still the size of S because they're shared across different U's. They're shared across different words, right? But and all of our previous use, most importantly, all of our previous use cases are unchanged, right? They all used V, and again, there's still only one V per word. So all of the previous use cases that I described are unchanged. Okay, so it's a recap over embeddings. Given training data to supervise, we want to model some property of the training data, like a Markov chain or skip-gram model. The goal of embeddings is to learn a low-dimensional representation over the data points, such that the geometry of this embedding preserves the property of the interest, right? The distance between the embeddings of songs preserves the distribution of the Markov chain. The inner product between the embeddings over words captures the model of the skip-gram model. Visualization semantics. Okay, my -1 minute. Sorry, going over time. Inner product embeddings have, in some sense, more interpretable axes, right? Because it's an inner product. But you can only really easily visualize 2 axes at a time. Distance-based embeddings, individual dimensions are hard to interpret because it's more the visualization tends to be more cluster-based, right? But it's easier to sort of visualize because of that. So next lecture, we'll be looking at deep learning, which can be viewed as a form of supervised embedding, and recitation this Thursday on advanced optimization.